This is a brief presentation of control engineering. Control engineering deals with modeling, analysis, and design. And for that, there are some concepts and some definitions that I will go over. And this is a brief outline. First, I will talk about linear discrete time systems, and I will define the transfer function. I'll talk about stability, what it means, and how it is checked. And I will talk about a design procedure called pole placement. I will give an example, and finally I will define what we mean by controllability and why it is important for design. Linear discrete time systems. Linear discrete time systems can be represented with a state model given by this difference equation, where x is a vector that represents the internal signals of the system, u is the input, and y is the output. Transfer function. Transfer function is the relationship between the input and the output in the z domain, and it can be given by this expression czi minus a inverse b, where I can go from the state model to the transfer function and vice versa. The poles of the system are represented by the eigenvalues of the matrix A, and they determine the stability of the system response. To illustrate this, we consider a first-order system given by xk plus 1 equals axk, where a is a scalar quantity, and the solution for this is obviously xk equals a to the power k x0. And depending on the value of a, the signal xk will decrease or increase. And what we want is that we want it to be decreasing all the way until it reaches 0. So we can see here very easily, because a to the power k will go to 0 if and only if the magnitude of a is less than 1. For higher order systems, it's the same concept, except that instead of the scalar a, I have a matrix A. In that case, the stability will depend on the eigenvalues of the matrix A. So we need all the eigenvalues to have a magnitude less than 1. Now we go to the design. The performance of the system depends on the pole locations. So obviously we need the poles to be less than 1, the magnitude to be less than 1, so that the system will be stable. But beyond that also, we can determine if the performance is going too fast or too slow, depending on the pole locations. So we can change the pole locations using what we refer to as pole placement. And for that, we can see here that the given model xk plus 1 equals axk plus b uk, and we introduce a feedback gain f such that the input is no longer an output, is no longer an external signal, but instead it is a feedback signal minus f xk. And that means that when we plug this in here, we get what we refer to as the closed loop model, where A sub c is the new matrix A, which consists of the original A, the original B, and the feedback gain F. Here we have an example. The example is simply second order, and we have the A and the B and the C, and we have the desired poles that we want in order to achieve the performance that we desire. And here the desired poles are 0.2 and 0.3. So we calculate the closed loop matrix A sub c equals A minus BF, and it is given by this expression after we plug in. But then this closed loop matrix A sub c will have a characteristic polynomial given by equation 1, and of course that characteristic polynomial will depend on the feedback gain f, represented by the components F1 and F2. The desired poles, 0.2 and 0.3, will also give us the desired characteristic polynomial, as in equation 2. What we need is equation 1 and equation 2 to be identical. And for that we take the terms of each equation and set them equal. So for that we'll take minus 0.5 to be equal to that and 0.06 to be equal to this. And we solve for F1 and F2 and we get these values, and that will give us the feedback gain. If we use that feedback gain in the closed loop matrix A minus BF, then we'll find out that A minus BF will have the desired poles. Another example. In this example we have the matrix A and the matrix B and the matrix C, but we will consider two cases for different desired poles. In the first case, we will have the desired poles given by 0.2 and 0.3, and we follow the same procedure as I explained in the previous example. We get A minus BF given by this, and that will give us the actual characteristic polynomial, equation number 3, and that's the characteristic polynomial that depends on F1 and F2, which are the feedback gain. On the other hand, we have also the desired poles, 0.2 and 0.3, and we get the desired characteristic polynomial, and we have equation 3 and equation 4. They have to be identical, so we take the terms from each equation and set them equal, and that means that I will have this equation, the first equation here, and the second equation there, but obviously I can see here that there's a contradiction. So the two equations conflict each other, which means that I cannot find values for F1 and F2 that satisfy both equations at the same time. So these two equations together do not have a solution. For the same example, I will consider a different set of desired poles. The desired poles here are 0.1 and 0.3, which will give me a desired characteristic polynomial given by equation 5. I'll do the same thing. I'll take equation 3 and equation 5 and set them equal. And when they are equal, I will have two equations because of the parameters of the equations. I will have two equations, and I will see here that the two equations are identical. So the two equations actually turn out to give me the same piece of information. So I do not have enough information to find F1 and F2. But I will have information to tell me how F1 is related to F2. So what I will do is that I will choose a value for one of them. Let's say I'll choose F2 to be 1 and use that value which I chose in either one of the equations, because they are the same, to find the other parameters. So choose F2 equal 1 and use that to calculate F1 to be 1.8. And here we say that the solution exists, but it is not unique. And it exists because the two equations, even though they are the same, but at least they do not contradict each other, like the previous case in part A. Now we have this block diagram that shows this here is the state equation, and then the output is equal to Cx, and we have the feedback gain coming from the state to the input, and that will give me the desired performance because I will have the new desired poles. But based on the three examples that we had, we can conclude that pole placement will succeed depending on how the state variables are connected to the input. And that's what we refer to as controllability. Controllability, as I just mentioned, is a description of the relationship between the input and the individual state variables, which means the individual poles of the system. To test the controllability of a model, we calculate the controllability matrix given by this expression, and we determine the rank of P sub C. If it has full rank, then the model is controllable. This here is a chart that tells me how controllability is needed for the success of pole placement. First, we check the controllability. If the model is controllable, then I can do the pole placement without any issue, and all the poles can be changed anywhere, and a unique solution will exist. But how about if the model is uncontrollable? If the model is uncontrollable, I may still have two different cases. To determine what will happen, I need to calculate the transfer function, because the transfer function will tell me where the poles are if they cancel with a zero. So find the transfer function HZ, and then find the poles that cancel with zeros. Those poles that cancel with zeros are the uncontrollable poles. And those uncontrollable poles cannot change. So if the uncontrollable poles are checked to be among the desired poles, then I don't have to change them because they are part of the desired poles. So if the answer is yes, then I will be able to have a solution, but the solution will not be unique. But how about if the uncontrollable poles are not among the desired poles? That means that the uncontrollable poles, which cannot be changed, are required to be changed because they are not part of the desired poles. So I will be asking for something that's impossible. So if the uncontrollable poles are not among the desired poles, then there will be no solution.